welcome to our physical sciences session. My name is Temba. Today we will be looking at redox reaction. What exactly about redox reactions do you want to actually focus our attention on? We want to look at, the different ways of interpreting redox reaction in terms of the species or the substances that are actually involved. It's going to be quite an exciting lesson, and you need also to pay careful attention also to the language that we use. It will be very, very, an integral part of our discussion for today. Right, now let's look at the overview in terms of how redox reaction, or where exactly redox reactions actually fall within the greater, knowledge area of chemical change. By now, we know that redox reactions consist of two half reactions, which is an oxidation as well as a reduction half reaction. And now the substances involved in redox reaction would either be your oxidizing agent or your reducing agent, but the combination of the two actually gives us what exactly happens in a typical redox reaction. Right. Okay. Now the thought that we want to throw out there, so that it guides us in terms of our session for today. The question says, have you ever looked at the same image and seen two possibilities that are both correct? So this has a lot to do with how you look at things. Consider perspective, right? Okay. Here is a simple example. Depending on how you look at this image, there are two possibilities. That is, if you look at it from this end, one may say, okay, this looks like a 6, okay, but if you try and look at it from that point of view, one may say it's a 9. Now, when we look at redox reaction, it entirely depends how you interpret, or your perspective, in as far as those half reactions or those redox reactions are actually concerned. So that's the big idea about how we look at redox reaction for today's session. Right. Okay. Now the terminology. Remember, when it comes to terminology, a greater component of chemistry, it's actually, embodied in, a language, which is the terminology. So when it comes to defining, it's very important for us to actually, understand that the examination guideline is our point of reference. Remember, you must understand the keywords, and also the context in which these keywords are used must be correct for you to earn marks for defining terms in chemistry. Right. Okay, so we will be talking about oxidation, reduction, and redox. Right. Okay, so exactly, what is an oxidation reaction? So in an oxidation reaction, the oxidation number, okay, of an element increases. Now, we know the rules by now of assigning oxidation numbers to substances. We know that if we talk about a pure substance, which is, an element in its natural state, its oxidation number is 0. So is the molecule, for example, with oxygen, right? So if we're going to keep track of what happens to magnesium in this reaction, between magnesium and oxygen, you'd realize that the oxidation number of magnesium changes from 0 to +2. So an increase in oxidation number indicates that the reaction is oxidation, right? Okay, and then also in an oxidation reaction, the element undergoing oxidation, now we're talking about the substance, in this case magnesium. So magnesium is actually the substance that undergoes oxidation. And when a substance undergoes oxidation, it actually loses electrons. So one way of looking at it, we can say magnesium lost. So this is the negative suggests that it's a loss, or we remove electron. So we're saying magnesium less 2 electrons, it gives us magnesium 2+. Okay, so if you come to think of it, this is actually an equation. Okay, so if you transpose the 2 electrons, and take it to the other end, we're still representing the very same process. Remember, the big idea to say, depending on how you look at it, there are two possibilities in as far as the 6 and 9 analogy is concerned. But now we are talking about a reaction that involves loss of electrons. Okay, so we can have a magnesium minus 2 electrons, that actually represents loss. But we can also say magnesium atoms when they lose, they give us a magnesium ion 2+ plus 2 electrons. We're still talking about the same thing, right? So in this case, all we are saying is that at the end of the day, we can represent the oxidation reaction in terms of magnesium to undergoing oxidation to give us magnesium 2+ and 2 electrons. So that's one way of representing, the oxidation half reaction, right? Okay. Now, what effect does the donation of electrons have on the overall reaction? So if something donates electrons or an electron, it actually loses the electron, okay? So the question that we want to pose at this point in time, what effect does the loss of electrons have on the overall reaction? Remember, the overall reaction is actually a redox reaction. That's what we want to arrive at the end of the day, okay? So this is the balanced equation of reaction. So the oxygen as a molecule of an element, according to the rules of assigning oxidation numbers, has an oxidation number of 0. But what has happened to oxygen? Something has happened. Oxygen now has an oxidation number of -2. What has happened to the oxidation number of electron? It has decreased. So magnesium donated, in other words, it underwent the loss of electrons, okay, to oxygen. So oxygen gained, okay? So in this case, if we talk about loss and gain, there is a transfer of some sort. Then we can therefore say oxygen gains electrons and is reduced. So the substance that gained undergoes reduction. That's what we want to arrive at now, okay? So in other words, we are saying that the oxidation number of magnesium increases from 0 to +2, okay? Now, magnesium loses electrons, all right? Therefore, magnesium undergoes oxidation. So in a nutshell, what are we saying? We are saying that a substance whose oxidation number increases is a result of that substance actually losing electrons. So the process undergone by a substance losing electrons is referred to as oxidation, right? Okay, and then also, we are saying magnesium donates electrons to oxygen. So the transfer is from magnesium to oxygen. So electrons are actually transferred between magnesium and oxygen in that direction. So oxygen gains electrons, so it is reduced, right? So magnesium has reduced oxygen. It's a different way of looking at it, okay? Now, we are also saying that a substance that undergoes the loss of electron is referred to as a reducing agent. So a reducing agent is actually a substance, right? Okay? Now, what about in a reduction reaction? The oxidation number of the element, in this case, which is oxygen, decreases. So conversely, or on the contrary, we are saying that a magnesium lost, and it was we refer to it as a reducing agent. Now, oxygen gained, we refer to it as an oxidizing agent. So in short, we are saying that a reducing agent undergoes oxidation, and then an oxidizing agent actually undergoes reduction. So the transfer is between the magnesium atoms and the oxygen, right? Okay, right. And then, so in a reduction reaction, the element undergoing reduction is oxygen, so it gains electrons, okay? So how do we represent that? We are saying that the oxygen ions actually gain electrons, right? Which is actually can be represented in a different way. Okay, so oxygen takes the electrons, but where are these electrons coming from? They are coming from magnesium. Hence, we are saying that the transfer is between oxygen and magnesium, right? Okay, so what effect does the taking of electrons have on the overall reaction? That's the big question now that we want to put across. Okay, so oxygen takes electrons from magnesium. So the magnesium loses, the oxygen gains, okay? We are saying the same thing. Oxygen gains electron and it is reduced. So reduction has to do with gain of electrons. All right. And then again, we are saying that magnesium has been oxidized by oxygen, right? The loss of electrons of magnesium can be attributed to the willingness of oxygen to actually gain. So oxygen is referred to as an oxidizing agent. take note of the terminology, very, very important. We can also keep track of, the oxidation numbers. For magnesium, the change in oxidation number is an increase from 0 to +2, while for oxygen, from 0 to -2. So there was the loss and the gain, right? Okay, so the loss of electrons is oxidation, and the substance undergoing oxidation is a reducing agent, while the gain of electrons is reduction, and the actual substance that gains electron is referred to as an oxidizing agent. So that's the long and short of it. Okay, so the terminology now that we arrive at is that an oxidizing agent is a substance. These are substances, okay? These are substances that undergoes specific processes, all right? So if we talk of an oxidizing agent undergoes reduction, right? While a reducing agent undergoes oxidation, right? So that's the main idea. So an atom or ion that causes another particle to be oxidized, so it's a substance, okay? It undergoes reduction. So an oxidizing agent takes electrons. That's the gain. That's the best way of trying to recall that. And then reducing agent donates electrons. So the equivalent of that would be RAD. So both of these are substances. All right. So this is the main idea in as far as this is concerned. So terminology plays a very, very critical role in terms of understanding the redox reactions. For now, we'll take a short break. When we come back, we'll delve more into some examples of trying to understand exactly what happens in a redox reaction. Let's take a short break for now. Welcome back to our session. We're still discussing the redox reactions. So we are essentially saying that, there are many different ways at which we may look at the same reaction. You can think of an oxidation half reaction in terms of loss of electrons or multiple electrons, or actually, a substance actually donating electrons. So both perspectives are actually correct, but then the language again plays a very, very critical role in terms of understanding exactly what happens at a particular level in as far as the electron transfer occurring between a reducing agent and an oxidizing agent. Now let's look at more of these tangible examples, right? Okay, so consider the following reaction between a metal and acid. By now, you should be able to remember that when any metal, a metal reacts with an acid, we get salt and water. That's the general reaction between an acid and a metal. Now, if for practical example, we can take zinc as a metal, this is a balanced equation between the reaction between zinc and hydrochloric acid. It gives us our salt, zinc chloride, and hydrogen. So the reaction has already been balanced for us. Now the question that we can put across at this point in time is, what type of a reaction is this? Is it an acid-base or a redox reaction? Now remember the 6 and 9 analogy. Can we think of this as an acid-base reaction, or we can think of it as a redox reaction? Now, one may, depending on how you look at it, both options, possibilities are actually correct. But now, let's look at exactly what happens in terms of the redox reaction, right? But also, one can think of this as a gas-forming reaction, okay? That's another possibility beyond just acid-base or redox, right? Okay, now, if we react zinc and hydrochloric acid, is this an acid-base reaction or a redox reaction? That's what we want to understand. But also beyond that, we are saying that if you remember the theories of, in terms of acids and bases, we know that an acid is a proton donor, a base is a proton acceptor. All these ideas come to mind. So depending on your perspective, you can think of this as an acid base, but how exactly is this a redox reaction? We've also mentioned that this could be thought of in terms of a gas-forming reaction because hydrogen gas is actually released, right? But we know this is an acid, okay, because it contains the hydrogen atoms, right? Okay. Right now, if we want to write down the oxidation reduction half reactions, let's keep track of what happened to zinc. Now, if you look at zinc, the oxidation number of zinc on the left-hand side is 0, okay? And of the same substance on the right-hand side is actually 2+, okay? Now, the oxidation number of zinc has actually increased. And what is it that we know by now is that if a substance, if its oxidation number increases, that substance has actually undergone loss of electron. So we can think of this equation in terms of zinc, undergoing oxidation to give us zinc 2+ plus, 2 electrons. So that's our oxidation half reaction, right? So that's our oxidation half reaction. What about the reduction half reaction? Now, if you look at hydrogen, for argument's sake, in this case, the oxidation number for hydrogen is +1, okay? It's actually +1, okay? And then on the right-hand side, according to the rules of assigning oxidation number, this is equals to 0, all right? So we can also immediately say, okay, hydrogen actually undergoes reduction. And how does that happen? We can simply say that 2 of these hydrogen, okay, plus 2 electrons, which were lost by zinc, it can give us H2. So this is our reduction half reaction, if you can think of it that way. So indeed, one can then safely say that this is a reduction half reaction. And also, you'd realize that for chlorine, it's -1 this side and -1 that side. So chlorine is actually not involved in the electron transfer. So these are the oxidation and reduction half reactions in as far as this reaction between a metal and an acid. All right. So we are happy with that. So if zinc undergoes oxidation from oxidation number 0 to 2+, we are saying zinc is actually the substance that undergoes oxidation, which is a reducing agent, okay? Okay, but there's something very interesting about hydrogen. We said, in as far as hydrogen is concerned, the reduction half reaction is 2H plus 2 electrons, okay, to give us the hydrogen gas, okay, in that sense. So the substance that undergoes reduction is the hydrogen ion in the acid. So this is our oxidizing agent, okay? So the oxidizing agent here is not the acid, it's actually the hydrogen ion. So if we were to write the formula of the substance, it would be H+. So the H+ is actually the oxidizing agent. Very, very important. So these are substances that undergoes specific processes, right? Okay? So if you think of a metal that has been displaced by hydrogen from the acid, this is a gas-forming reaction, as we have said, okay? So if you go back to that equation, you see that the zinc has actually displaced the hydrogen, okay? If you want to think of it that way. So the acid becomes the salt according to that general reaction, right? Okay, and also you're saying that the metal is the reducing agent. Why? Because it undergoes oxidation. So the process undergone by this reducing agent is oxidation, while the hydrogen in the acid, very, very important, is the oxidizing agent, because the hydrogen is the one that underwent reduction, okay? Very, very important piece of information, okay? And then the question, do all metals react with acid to form hydrogen? That's the big thing. Now we want to look at these displacement reactions. For argument's sake, if we take magnesium and zinc, okay, magnesium does displace the zinc, all right? So this is a possibility. So yes, is this a redox reaction? Indeed, because magnesium from 0 to +2, magnesium underwent what you call oxidation, and then zinc from 0 to from +2 rather, okay, +2 to 0, it underwent reduction. Is this a redox reaction? Yes, it is. All right. Okay. Now, is this a redox reaction? We agree, because magnesium actually underwent oxidation to give us Mg2 plus 2 electrons. Okay, while zinc 2 plus gained electrons to give us zinc metal. Okay, so yes, indeed, this is a redox reaction. So we can actually do that. These are the half reactions that we are talking about. Okay, so which talk about the transfer. Okay, and then again, identify the oxidizing agent and the reducing agent. So this substance that undergoes oxidation is our reducing agent. Okay, while this substance which undergoes reduction, so this is the zinc ion, all right? This is our oxidizing agent, the one that undergoes reduction. Okay. Okay. So it's all about the terminology. So magnesium displays zinc from the solution. Yes, according to that reaction, we've managed to arrive at that. Okay. Now predict what would happen. Is zinc going to displace magnesium? Definitely not. This reaction will not take place because magnesium shows a greater willingness, to lose electrons than zinc. All right. And then zinc cannot displace magnesium from the solution. So what does that say? It says to us that magnesium is actually a stronger oxidizing agent than zinc. Right. Okay. Now, if we talk about the strength of a substance, so if we have a magnesium chloride, so already here magnesium is magnesium 2 plus, while zinc has an oxidation number of 0. So if we compare the relative strength, it says to us that this reaction will not take place. But why does this reaction not take place? Because if we compare what we call the strength of a reducing agent, first of all, the big question that we need to ask ourselves is, what exactly is a reducing agent? It's a substance that shows, more readiness or willingness, rather, to donate electrons to another. So if you compare zinc and magnesium, we arrive at a point that, no, actually magnesium is more willing to give to zinc than the other way around. So we are saying that magnesium is a stronger reducing agent compared to zinc. That's the main point. So which explains why this reaction does not take place. So as a result, we are saying that magnesium is indeed a stronger reducing agent than zinc by comparison. Okay, we'll take a short break for now, and then when we come back, we'll look at more examples in as far as redox reactions. Let's take a short breather for now. Welcome back to our session. We're still talking, working with redox reactions. So we now have identified the fact that we are able to, look at a redox reaction, from different perspectives, using practical examples of reactions that involve metal and acids. Or you can think of the same reaction in terms of the transfer of electrons. Now we'll try and look at more examples of that and see how exactly we can, try and identify the role of different species, in terms of your oxidizing agent as well as your reducing agent. Right, so now we want to also compare the reduction potential in terms of the two substances involved, one being able to readily donate, the other one being able to actually readily accept electrons in terms of the standard reduction potential. So this is some kind of a reactivity series of some sort. Now let's look into that. Okay, now we understand that displacement reactions have to do with the comparative strength between, two substances. Say, for argument's sake here, we're comparing, magnesium and zinc, in the context of a reaction between a metal, okay, and a salt in this case, right? So these are displacement reactions. So our comparison is confined to magnesium and zinc. So we are saying that magnesium has displaced zinc from the solution. The solution that we're talking about in this case is zinc chloride. Now, why are we saying magnesium has displaced zinc, you'll see that in the solution now we have got magnesium chloride instead of zinc chloride, and then zinc actually is produced as atoms. At the end of the day, we can say that magnesium was able to displace the zinc. Right. So, or if you can think of displacement in terms of substitution, where there was zinc, now there is magnesium. That's what we exactly mean when it comes to the displacement. Right. So the half reaction, which actually shows the reduction, is that zinc ions in solution are reduced. The process is reduction. So these zinc ions in the solution are actually our, zinc ions are our oxidizing agent. Okay? So this oxidizing agent is actually the substance or the species, the ions that undergo reduction. All right. Okay. And then let's look at this one. In this case, we've got copper chloride solution. All right. So say for argument's sake, we've got a solution of what? Of copper chloride. Okay. Right. So in this copper chloride, which ions are present in this solution? We've got the copper ions, all right, as well as the chloride ions. Very, very important. And then if we put some zinc metal into this, a reaction will take place. Okay. But essentially, what is happening here, zinc has displaced the copper, all right? That's why at the end of the day, in solution, we now have zinc chloride. So what role does zinc play in this reaction? Now we understand that zinc atoms undergo oxidation to give us Zn2 plus 2 electrons. Now zinc being the substance that undergoes oxidation, then zinc becomes our reducing agent. Okay? So zinc is more willing to because zinc undergoes oxidation, it is more willing to lose than copper. That's why zinc is able to displace copper in solution. So it is a reducing agent, right? And then now we are saying that zinc is the reducing agent because it undergoes oxidation, okay? So this is the process. So in a nutshell, we are saying that zinc is more willing to lose electrons compared to copper. Hence, it can be explained by this half reaction that we see below, right? And then also, we are asking ourselves, okay, what if we compare zinc in these two reactions? Now, we can do so by way of tracking the changes in the oxidation numbers. So in reaction 1, zinc undergoes, because here the oxidation number is 2+, zinc undergoes, let us put it this way, okay? This is what we are saying, okay? Zinc ions are actually reduced to give us zinc metal. So this is plus 2 electrons. This is for reaction 1, all right, Zn, right? But in the second equation, zinc undergoes oxidation. So it means Zn, okay, to give us zinc ions in solution plus 2 electrons. Now we're looking at the same substance in two different reactions. Now the question is, what happens to zinc in the two reactions? By now, what is it that we know? We know that a substance that shows a greater willingness or readiness to lose electrons is actually a stronger reducing agent, okay? So on the same note, we are saying that if a substance is a stronger reducing agent, you can think of it as being a weaker oxidizing agent. We are saying the same thing depending on how you look at it. But if you look at it in terms of losing electrons, it's a stronger reducing agent. In terms of gaining electrons, it's a weaker oxidizing agent. But in two reactions, the same substance undergoes two different reactions, right? So the spectator ions in this case, if you come to think of it, if you look at chlorine on the left here, it's -1, -1. So chlorine is not involved in the transfer of electrons. That's why I would refer to it as a spectator ion, right? So in reaction 1, zinc is actually undergoing a reduction, which is the gain of electrons, right? Now, if we look at it in the second reaction, zinc undergoes oxidation. So in summary, two things may happen to zinc. The double arrow there shows us that there is a possibility for zinc ions to be reduced or for zinc atoms to be oxidized. So you may choose to read this equation from left to right or right to left, depending on the reaction in which zinc is actually involved. So remember the analogy of the 6 and 9. We're still saying the same thing. It entirely depends in terms of with which substance are we comparing zinc. So the double arrow suggests that there are two possibilities here. If we read this equation from left to right, we can have zinc 2 plus 2 electrons to give us zinc, okay? Or from right to left, we can show zinc undergoing oxidation, okay? Plus 2 electrons, right? So that's the main idea, okay? So that's what it means. So if you compare the strength of reducing agent, displacement reaction, they actually provide a method for establishing a list of metals in the order or a sequence from the strongest to the weakest reducing agent. So a stronger reducing agent will actually show greater willingness or readiness to lose electrons, okay? Now this list, we call it the reactivity series, which is not entirely new to us. So we can write half reactions as reversible reactions, okay, which explains the double arrow that we saw was the example with zinc in those two different reactions, right? Okay, now we are also saying that magnesium is able to displace zinc, and zinc is able to displace copper. So if we are to put this in a sequence or in that reactivity series, so the element at the top, the substance at the top, shows greater willingness to actually displace another one. So we can think of it in terms of that trend or that sequence, right? And then we ask ourselves, where does silver belong in the reactivity series? So if we go back here, okay, you realize that magnesium can displace zinc, zinc can displace copper. Now, according to this reaction, copper can displace silver, okay, because now we have got zinc ions in solution. Now, we ask ourselves, where does silver belong? We are able to locate silver as per this equation to say because silver can actually be displaced by copper, we can then arrive at the thinking that copper is actually above silver in terms of the reactivity series, meaning that copper, zinc, actually magnesium is the strongest reducing agent of them all. As a result, we are able to come up with this series, whether you look at it from top to bottom or bottom to top, right? So these are some of the ideas that we actually need to try and understand. So if we think of different elements, we can think of hydrogen in terms of the reactivity series. But then these are some of the, the thinking in terms of comparison of the reactivity series, which is something that I would also want to look at after our short break, and then we'll try and discuss more examples and look at the standard reduction potential tables. For now, let's take a short breather. Welcome back to our session. We're still working with redox reaction. Now we have arrived at a point where we appreciate that there is a reactivity series that we can use, as a way of comparing, the relative strength of different substances in terms of their reducing ability or their willingness to actually lose electrons in the transfer process, which happens in a, typical redox reaction. Now, let's look at another example, okay? But before we do that, the table of standard reduction potential, what exactly does it do? instead of us using the displacement reaction, because in a displacement, we are saying magnesium displaces zinc. So in other words, zinc is a stronger reducing agent compared to magnesium. So instead of using these displacement reactions to actually establish the order table of reducing agent and oxidizing agent, the chemists actually can measure the extent of reduction using the electrochemical cells. So these electrochemical cells is a way of actually trying to get to a point where you are able to compare different substances in terms of their reducing ability. And also think of it, we can talk of these substances in this standard reduction potential table in terms of their reducing ability or in terms of their oxidizing ability. Because we are saying that, by all means, a stronger reducing agent, if it's compared to another substance, it is actually a weaker oxidizing agent. And the opposite is true for those two substances that are involved. So the displacement reaction actually gave us a way of trying to measure or compare, the relative strength of different substances in terms of their reducing ability. Right. So this is the table of the standard reduction potentials, okay, of different substances. So if you look at the arrow on the right-hand side, it says to us increasing reducing ability. So what are we saying? We are saying that lithium is a stronger reducing agent compared to, say, for argument's sake, if we compare lithium and potassium compared to potassium. So we are saying that lithium can displace potassium in that order, right? Okay. So this is the different substances now listed in the sequence or in the series in terms of their reducing or oxidizing ability, right? So hence we are saying that if you look at it from top to bottom, it's in terms of oxidizing ability. But if you look at it in terms of bottom to the top, it's in terms of reducing strength, okay, or reducing ability. So we are saying that the reducing ability actually increases as you go up that series, and the oxidizing strength of the substance actually increases as you go down the series, right? Okay, now we want to make use of this table of the standard reduction potentials to actually write balanced chemical equations for the reaction between aluminium and iron 3 oxide, right? So we will make use of the table, okay? Now, this is the table. The substances that we are interested in is actually iron 3, okay? And so this is our iron 3, as well as our aluminium, right? There is our aluminium, okay? Now, if you look at this table from top to bottom, it says as you move up that table, the strength of reducing agent increases. We are saying that the topmost substance actually shows greater readiness or willingness to actually lose electrons. Why lose electrons? Because we're talking about its reducing ability. And a reducing agent actually shows greater readiness to donate or lose in the process undergoing oxidation, because that's what exactly a reducing agent actually does. It undergoes the loss of electrons, right? So if we are to do that, we are saying that aluminium is a stronger reducing agent than iron. So we can represent the top equation, because that says the equation can be interpreted left to right or right to left. So in this case, it's going to be aluminium undergoing oxidation. Now it goes in one way because the comparative strength of the two. Then we get aluminium ions plus 3 electrons, right? While the one below is going to be iron 3 plus 3 electrons to give us aluminium ions. So the first half reaction would refer to it as we have seen in the previous example as the oxidation half reaction, while the one below is the reduction half reaction. But of particular interest to us, again, is the role of each of these. So aluminium is a stronger reducing agent, okay? All right. While the iron 3 is an oxidizing agent. So these are the two half reactions that are undergone in this reaction between iron and aluminium, right? So if we are to do that, we can also say, okay, these are the half reactions. So, but we want to write a balanced reaction for both of them. So the number of electrons lost by each aluminium is 3. And then for every Fe3 plus ion, there are 3 electrons gained. So what is lost equals to what is gained. So we can simply say, in terms of the net ionic equation, we'll have aluminium, okay, plus ion 3, okay. Okay, we made a mistake here. I think we need to have, just to correct that, we can't have aluminium on the second one. Okay, take note of that, you know, because it's just an oversight. So we will have ion instead, okay? So if this is going to give us what? Aluminium ions, okay, plus ion. So this is the balanced equation of reaction. Okay. We can also look at different examples by making reference to the standard reduction potential tables. But if we are to keep track in terms of balancing, let's also pay attention to the electrons involved in each of those half reactions. So this reaction involves hydrogen sulfide and potassium dichromate, right? Okay. So if we are to look at hydrogen sulfide, we have to identify the reaction involving hydrogen sulfide. In this case, this is the reaction that we're talking about. So this table will actually be given, you know, even in an exam. Yours is just to understand how to use it and which equation is relevant depending on the question that is given. So you don't necessarily have to memorize all these equations. It's quite a lot of it. So understanding is very, very key, right? So this is the first equation. Now we are going to compare it because the table is it's quite long, and then there is the second part of it that involves the dichromate. There is the half equation concerned, okay? So already we are seeing that the dichromate reaction is bottommost. So it means this dichromate one actually has to do with the reduction, because it is saying as you go down the table, the strength of oxidizing agent increases. While if we can go back, as you go up, the strength of reducing agent will actually increase, all right? So at the end, it gives us that. So we want to understand that, okay, the hydrogen sulfide is actually our reducing agent as per the table. So if we were to rewrite this equation, we'll have our hydrogen sulfide, okay? Take note of the formula, which is a gas, okay? Undergoing oxidation to give us sulfur atoms, okay? The hydrogen ions in solution, okay, plus 2 electrons, right? And then the dichromate one, but take note again, the symbol now is left to right. The dichromate one will be Cr2O7, 2 minus, plus 14H plus. So this 14H plus tells us that this half reaction of reduction occurs in an acidic medium, plus C electrons, 6 electrons. So the 6 electrons are actually gained, which gives us the reduction half reaction to give 2 Cr3 plus, okay, which goes into solution, plus 7 water molecules. Right. Now, these are the 2 half reactions. So that's our oxidation and that's our reduction. So this is our oxidation half reaction, and the below one for the dichromate is our reduction. So for us to balance the number of electrons, the thinking is whatever is lost must be equal to what is gained, which is also equal to what is transferred between the reducing agent as well as the oxidizing agent. So if you check here, I think even from a simultaneous equation, to actually balance the electrons, we can multiply this by 3 and this one by 1. So as a result, we'll have the equal number of electrons becoming 6 lost, 6 gained, right? So if we do that, obviously the electrons will cancel themselves out. Now, if we multiply this by 3, then we'll have 3 hydrogen sulfide, okay, plus, okay, the dichromate, Cr2O7, 2 minus, okay, plus 14 hydrogen ions, okay, to give us 3 sulfur, okay, plus, if we multiply that by 3, it will give us 6H plus, right? Plus, if we multiply the chromium ion 3 plus, it will give us by 1, it will give us 2 Cr2 plus, okay, plus 7H2O. All right, okay, but you'd realize that on the left, we've got 14 hydrogens and we've got 6 on the right. So you can immediately say, okay, actually the hydrogen ions will remain on the left because we've got 14. So if we subtract that, we actually get 8. So we can actually get rid of those ones on the left-hand side and actually say, okay, we are left with 8. So this becomes our balanced equation of reaction, okay? So, okay, that's our balanced equation of reaction. So this is how we actually use our standard reduction potential tables. So in summary, what are we saying? Redox reactions actually involve the transfer of electrons. So in the transfer, there's the loss and the gain. These happen simultaneously or at the same time. And also, in every redox reaction, there is an oxidizing agent, the substance that loses, and a reducing agent, the substance that actually gains. So, and overall, the table of the standard reduction potential is an order of list of these half reactions in terms of oxidizing agent and reducing agent. I think beyond these few examples that we have used, I think it's very important to emphasize that a lot of practice will actually go a long way in terms of getting into grips and understanding the concept behind, of what happens in a typical redox reaction. With that said, that's the time we had for today. Goodbye for now.